Welcome back, College Algebra students. We are now in Chapter 6, Section 4. In this video, we will be taking a look at logarithmic functions. So our objectives are on the screen there as far as what we're going to be looking at. We're going to be changing exponential statements to logarithmic statements and vice versa. We'll also change logarithmic statements to exponential. So somehow those are going to be connected. So our last video was on exponential functions. This one's on logarithmic, so they're going to end up being related. Number two, we'll evaluate these logarithmic expressions. We'll determine their domain of a logarithmic function. We will graph them, and we'll also solve them. Okay, so without much ado, let's go into the definition. So the definition of a logarithmic function with base a. So the logarithmic function with base a couple caveats here. A has to be bigger than 0, and a cannot be 1, is denoted as y equals the logarithm with base a of x. And we know that's how I just read that. So the logarithm of base a with x, or sometimes instead of saying logarithm, we just abbreviate it log. We got log of base a of x. Okay? And so we have our definition here, or in symbols, y equals log of base a with x, if and only if. So what this means then is that x equals a to some exponent. So the logarithm equals then an exponent. This y value is the exponent we apply to a to get to x. So a is our base. A is written a little bit lower. Think about a basement. The basement's the lowest part of the house. The B is our base, or our base here. And so in this case, A is representing our base. So we have our base to some power equals x. So sometimes one way to write this is this way. If I roll back around, a to the power of y equals then x. Okay? So that is our overall statement as far as what a logarithm means. Now this also works in reverse. If x equals a to the y, then we can say the log of a with base x is y, because y is still going to be the logarithm. Now, by definition, also the domain of the logarithmic function of y equals log of x base a is going to be x greater than 0. Okay. And so as we look about that, it is in the definition here. Hopefully this makes sense. If a here is bigger than 0, okay, and we're saying what we have here is that a raised to some power is x, okay, so a raised to some power is x, so a raised to some power is going to be x here. What are we allowed to choose for x? If a is positive, okay, then and we raise it to a power, well, a to a power, any positive base raised to power, is always going to end up being positive, because what does the exponent tell us to do? It means multiply the base a certain number of times. So if we're multiplying a positive by a positive, doesn't matter how many times we multiply, it will always end up being then positive. So even though it is in the definition here, hopefully it does make some sense. So our domain of the logarithmic function is all x values greater than or equal to 0. So our domain in interval notation is negative infinity to infinity. So as this definition illustrates, a logarithm is a name for a certain exponent. That's from our textbook. What we would like to phrase, or one way we can think about this, and I like the way the book phrases, so I actually just copied it right out of the textbook here. When we need to evaluate log of x base a, or log of base a of x, depending on how you want to phrase that, we want to think about a raised to what power gives me x. Okay, so a raised to what power can do that. That's the thing that we're looking for. So if I have log of, say, 8 base 2, okay, and I want to see, well, what is that? I'm going to say 2 to what power? So 2 to what power gives me 8. That's the idea. And if familiar with our exponents, well, 2 cubed is 8. So that would mean log of 8 of base 2, or log base 2 of 8, okay, is going to be 3 then. Okay, so that item here would be 3, because 3 is the exponent we'd apply to our base 2 to give us 8. Let's take a look at changing these and rewriting these items in their particular forms. So the first thing is, let's change these exponential statements to an equivalent statement involving a logarithm. And then we're going to reverse that in example 3. We're going to take our logarithmic statements and we're going to rewrite them as exponential statements. So if we have our statement up here, Let me write it down. We've got log or y equals log of x base a, or log of base a of x. And so what that means then, let me do it this way. We come back up here. That means x equals a to the y. So we're just rewriting all of that down here and vice versa. So the arrow can go both ways. So that's the overall idea that we're referencing. Let me clean my item up here. So we've got a to the y. Looked like a b there. So a to the y equals x. So here's what we have. So 1.2 cubed equals m. So we've got a logarithm. Okay, our logarithm is going to equal the exponent, which is 3. Our base was 1.2, and our value is m. So the log of m with base 1.2 is 3. So what exponent, let me rephrase that. So 1.2 to the power of 3 equals m. What power do we have to raise 1.22 to get m? Okay, and so we rewrite this. One other way I like to show this is that we just start with our base and loop around the other side. 1.2 with m then equals 3. Over here, we reverse this over here. We would say log of base e of 9 equals b. So the e, pick up the 9, land on the b. Just a quick kind of visual way to try to describe this. But what we're saying is we have a base of e. Our exponent is what our log equals. And then our other value here, our value after we had taken our exponent, is going to be 9. On c here, if we do this same way, our logarithm has to end up equaling 4 because the log is the exponent. And so our base was a. And so we're of 24. Log of 24 of base a, or log 24 of base a, is going to end up being 4 here. Again, if I kind of do this little loop-de-loop, start with my base, pick up the 24, land back down on the 4. If I take these and go the opposite direction, log of 4 base a is 5, or log base a of 4, depending on how we want to phrase that. And so I can say, okay, so a to what power gives me 4? So a to the power of 5 must give me 4. And over here, log of base e of b is -3. So we would have, let's see, we have our base. Our logarithm then is our exponent. So e to the -3 then is b. On this side, we have 3 to the power of c must be 5. Again, I can pick it up this way. Start with my base, pick up the other side as the exponent, land back down on this other piece. E to the -3 lands on B, 3 to the C lands on 5. So that is one way to go ahead and think about those. But again, we're just doing the same overall concept, same idea as far as we're moving from one definition to another overall. We can evaluate logarithmic expressions. Let's find the exact value of these items. So we have log of 16 base 2. What we're asking then here is 2 to some power. Let's call this x. 2 to some power has to end up being 16. That's the thing that we're trying to find. We got to figure out, well, what power is that? So if we wanted to, we could go ahead and off to the side and say, okay, well, yeah, log of 16 base 2 has to be something, so we can rewrite it in the exponential form. In our exponential video, the last thing that we did in that video is we solved equations like this. And we said if we can get these bases to match, then whatever the exponents are also have to be the same thing. So let's see, I need to get the same basis. So 2 doesn't reduce any further, but 16 does. Okay, can I get 16 as 2 to some power? Let's see, 16 is 4 times 4. 4 is 2 times 2. So 16 is really 2 to the power of 4. So 1, 2, 3, 4 2's. So that means 2 to the x is the same as 2 to the 4th. So since my bases here are the same, that means the exponents must match. That tells me x is 4, meaning then that the log of 16 of base 2 must be 4. And 4 was the value I was looking for. Do the same thing with letter B here. So let's say that's got to be something. So we'll set that equal to x. We could set it to A, B, C, D, whatever variable we want. X is very frequently used. So I'll go ahead and stick with x here in this case. So I'm going to say 3 to some power. What the logarithm means is our base to some power has to be this 1 over 27. Now, as we take a look at this, I need to get these bases to match each other. I need to get the 3 and the 27 to match. So let's see, if I take 27, that's going to be 3 times 9. 9 breaks down to 3 times 3, so 27 is 3 cubed. However, this is 1 over 27, so 1 over 27 would be the same thing with a negative exponent. So I have 3 to the x equals 3 to the negative 3. So now my bases match each other. Since my bases match, now my exponents I can set equal to each other. So x must be negative 3, meaning then that the log 1/27th of base 3 must be negative 3 then. So negative 3 was the answer that I was looking for. Now, sometimes people ask, can I do this in the calculator? And the answer is yes. Let me go ahead and show you the calculator and how we can do these. So we wanted the logarithm, okay? Let's see, when the logarithm of 16 base 2, okay? So if I just go up here in my calculator and hit log, I don't see a base value here. So let me clear this out. There's several things we can do in order to see this. One is we can go to the math button. If we go to the math button and arrow down, whoops, or if we're at the top, we can arrow up. Letter A is a log with a certain base. Okay, so I'm going to stop on that piece and click that button. Now I see my math print, I have this so I can do what I want. So I wanted log of 16 base 2. So my base was 2, and then I arrow over to get 16 here. Now we already said that that answer should be 4, and our calculator comes up with the same thing. So we went to the math button and then down to or up arrow, I guess maybe quicker, go to log base. The other way to do that is hit the alpha button. And if we go up into y equals, we see other commands up here. So we have fraction, functions, matrices, and y variables. We want to go over here to functions, which is the window. And in here, we also see some other things that might be of interest later on at some point. What we're interested in is number 5, which is the log base. So we just type 5. And then we can do the same thing. So log of, let's see, it was the next one was log of base 3 with 1/27. And we ended up with negative 3 also. So the second way to find out was the alpha key, alpha window, and then log base was the item we were referencing. Now, if you have an older TI-84 calculator, maybe a TI-83, then all you have available, you're not going to have that log base. The log base function is a little messy. So what you can do is we can do just log. If I want to do log of 16 with base 2, I'm going to do the log 16 first, close that off, and then divide by log base 2, not log base 2, but log of 2, close that off, and we still end up with 4. So 1, 2, 3 different ways at least that we could figure out the logarithms on our calculator if we're trying to figure out just a numeric value. So I wanted to show those that you had access to that and you could see that. So determine the domain of a logarithmic function. So we already had said that domain was going to end up being all the positive values. Okay, I believe we had said that already. I was just looking back in the notes. Did we say that up here? I believe we had that up here just a minute ago. Yeah, in the definition, the domain of the logarithmic function is x greater than 0. Okay, whoops, greater than 0. And I just caught this silly mistake here. If the domain is bigger than 0, that's not negative infinity to infinity. That's 0 to infinity. My mistake there. Glad I went back up there to catch that. If you had already seen that and jotted down the notes to email me and let me know, thank you. But our domain should be all x greater than 0. So we're going from 0 to infinity. And our range is going to end up being from negative infinity to infinity. Okay, so what are the y values that we end up with? So what y values can we choose as far as our exponents on a? Well, there's no limits on or restrictions on what we can use as our exponent. And since our exponent is our y value, and the y value represents our range, then the range has no restrictions. It's from negative infinity to infinity. So as we take a look at that, we will do a graph here as one of our next examples coming up. But what we want to see first off is we just want to go ahead and take a look at some functions here, and we want to find the domain. Okay, so we're going to end up finding the domain of each logarithmic function. And remember that our x value has to be between 0 and infinity. So where our x position, okay, notice in our definition up here, x is this spot. Okay, so that spot, okay, highlighting this again, this spot here must be bigger than 0. That means in question A here, capital F of x is log of x plus 3 with base 2. That means this position here, that position has to be bigger than 0. Okay, so if that position has to be bigger than 0, then that means x must be bigger than -3. So then my domain are all x's such that x is bigger than -3. If we take a look at letter B, we have g of x is a log, and so this position in the logarithm must be positive. So that position in the logarithm has to be positive, and we got 1 over x over 1 minus x must be greater than 0. So when is a rational inequality bigger than 0? So what we need to do then on this one, if we go back to our rational functions, is we need to take a look at the key pieces here. So when does our numerator go to 0, and when does our denominator go to 0? So our numerator goes to 0 at -1, and our denominator goes to 0 at 1. So if we take a look at that, we've got -1 and 1. So what we're going to do here then is our sign graph. So we're going to take a look at what are the signs of 1 plus x over 1 minus x in these three different regions. So we know at -1 and 1, we have certain values as far as things that take place. We were only interested in when is it positive, so when is it above 0. So if we're out here less than -1, let's say it's -4. Well, 1 plus -4 is a negative. And 1 minus a negative, so that means makes it 1 plus something, that's going to be positive. So we got a negative divided by a positive, which is negative then overall. That's not what we want. Let's go from -1 to +1. Choosing a value in here, let's choose 0 because that's just easy to work with. 1 plus 0 is 1, which is going to be positive. 1 minus 0 is 1, which is positive. So positive over positive is a positive. And let's choose something out here beyond 1. How about 10? 1 plus 10 is definitely going to be positive. 1 minus 10 is going to end up being negative. So a positive divided by a negative is negative. So the region that we want is in here in between -1 and 1. Now, since at -1 and 1, it was either undefined or 0, then what we want is we don't want -1 or 1. We want our x to be in between those. So our domain then, we want, whoops, not F, D. D here, there we go. Our domain are all the x's such that -1 is in between, not less than or equal to, in between. So x is in between -1 and +1. If we have that, then our function is defined. Taking a look at letter C. Again, what we're referencing is this position here. That position has to be positive. Okay, so this item overall, let me circle that piece. So what we want is we want the absolute value of x to be greater than 0. Well, that will happen all the time as long as x is not 0. Because what the absolute value function is what are the values or what are the distances away from 0. If we do a quick graph here, if we remember back from our library of functions or parent functions, this was the absolute value function. It's going to be above the x-axis, so it's going to be positive everywhere except at 0. At 0, it is 0. So our domain on this one are all the x's such that x is not equal to 0. Okay. Now, if we were trying to write that in interval notation, that would be -infinity up to 0. Union with 0 out to infinity, and sometimes instead of the union symbol, we just write a comma. So we have 0 is a thing we're not allowed to have. So we don't include it on the left piece here, and we don't include it over here on this right one. If just for sake of example, I was doing the interval notation back over here, it would have been negative, which is not -infinity, -1 up to +1 would have been that interval notation. And over here, the interval notation on this one would have been x bigger than -3, so -3 out to infinity. So it depended on how we're writing our examples and how we're writing our answers, we could end up with a slightly different notation. So we have talked about the domain and range of a logarithmic function. So we're saying up here, our domain is going to be positive, and our range is going to be all real numbers. So as we take a look at a graph of that, and so as we would take a look at the graph, okay, what we have is we have two graphs on each of these. We have in blue here, we have an exponential function, y equals a to the x, okay, and then we have the corresponding logarithmic function, log of x base a is y. So if we take a look at these two and we graph it across the line y equals x, okay, then what we see is that we have the inverse functions. So if 1a is on the graph, a1 is on the graph of the inverse. If 0, 1 is on one graph, 1, 0 is on its inverse. -1, 1 over a is on a graph, 1 over a, -1, it would have to be on its inverse. So we've not really defined it as the inverse as of yet, but that really is what it boils down to. If I take a look again at y equals log of x base a, that means a to the y power has to be x. If I would take a look at trying to graph that, okay, then I have x, okay, so x equals a to the y, looks like a b there, sorry about that, a to the y, and then I have my actual y value. So what's interesting about these is my x is really dependent on y. Normally, our y is dependent upon x. Tell me an x value, then I can calculate the y value. In this scenario, tell me the y value, then I can tell you what x is, because x has to deal with a to some power. So for instance, if I choose -1 for y, then x is a to the -1, which is 1 over a. If I let y be 0, then a to the 0 is x, and a to the 0 is 1. And when y is 1, I have a to the first, which is just a. So these are the points that I have, and that's what these points are over here. This first point was 1 over a -1, 1, 0, and a 1. So that, as we see, then would be the inverse of the exponential function of a to the x. And so if we take a look and plug some actual values in here, okay, I guess not some values, but if we go ahead and reverse this a little bit, so if a is less than 1, okay, if a is less than 1, then we just reverse these a smidgen here. So they're going to end up getting flipped. Okay, same way with our exponential function. So this first side was when a is bigger than 1, so we had exponential growth. So our exponential growth function goes up here, and then our logarithmic function starts at -infinity and then goes up. If we have exponential decay, where we start at infinity and come down, then our logarithmic function also starts at infinity and comes down. Kind of like over here, we're close to 0 and then go up to infinity. So we start, instead of at 0, we start at -infinity and we come up towards positive infinity. So kind of some fascinating pieces as far as how these are set up. So let's look at some properties here. So the properties of the logarithmic function, okay, when a is positive and a is also not equal to 1. The domain is a set of positive real integers that have to be positive using interval notation. The range then is a set of all real numbers, or an interval notation, -infinity to infinity. The x-intercept of the graph is 1, whether we were growing here, okay, or whether we were decaying over here, the x-intercept in both of these ended up being 1. Further, okay, there was no y-intercept. We never crossed the y-axis. Okay, the y-axis, however, so x equals 0, is a vertical asymptote of our graph. So our logarithm never gets to, as far as our x value can get really close to 0, but we never actually touch it, because remember, for our domain, x, we want all x is such that x is greater than 0. So in interval notation, that's at 0 out to infinity. So we get really close to 0, but we don't actually get there. So that's going to end up being our vertical asymptote. Okay. Further, the graph of, up here on this point here, logarithmic function is decreasing if a is between 0 and 1. Okay, just like we had an exponential function, if the exponential function is between 0 and 1, we're at a decay. Our logarithmic function will also be decaying or decreasing as well. If in an exponential a is bigger than 1, we had a growth, then in a logarithmic function, we will also be increasing. So the logarithmic functions and the exponential functions take on a lot of those same characteristics. Our logarithmic functions will also contain the points always, 1, 0. Our growth factor with a, or the base of our logarithm. So in our exponential function, it was our base of the exponential. In our logarithmics, it's the base of the logarithm. Okay, so similar kind of ideas. So 1, 0, base 1, 1 over a with negative 1. When we're doing the exponential, when we're doing the exponential, it was 0, 1, 1a, and negative 1, 1 over a. Okay, so at negative 1, 1 over a, 0, 1, 1a in the exponential, and in the logarithmic, they're reversed. So again, it shows us that it's following the properties here, that the logarithmic function and the exponential function are inverses of each other. And this graph is also smooth and continuous. We have no corners and we have no gaps. Okay, so those are the properties of the logarithmic function. If the base of our logarithmic function is the natural number e, okay, then we say we have y equals ln of x. Okay, so let me go ahead and move this down just a little bit here. So if we have y equals log of x base e, we can rewrite that as y equals ln of x. So the natural log, or the log of the natural number, okay, so log of base e, log of the natural number, ln, appears so frequently we have a common abbreviation. That abbreviation then is ln. Now, very consistently, I like to write my natural log as either capital Ln, or I'll do cursive with ln. Because if I write this, sometimes I get confused. Is that supposed to be one n? Okay, so the typeface that we use, in my opinion, makes a big distinction in here. So I like to typically write capital L with the N, just to go ahead and make that distinction. So everything else remains the same then. So what we would say is if y equals the log of x base e, implies then that we have e to some power equal to x. Okay, so same thing that the text is saying. I just reverse my lefts and right here, and these go back and forth. So e to the y would have to end up being x. So if I have a natural log, if I have the natural log, I know that my base then must be e. Now that's going to be different from something that we see later on. If I see log of x equals y, what that means, if I don't write the base, that means log of base 10 equals y. And so that's going to mean that we have 10 to the y is going to end up equaling x. Okay, so this is the log of base 10. 10 is so common, we actually call that the common log. So we have two special logs over here. We're going to get to the common log here in one of the next examples, but I'll bring it up here at this point just to illustrate that we do have two special logarithms that we use very consistently. So one is a log with base e, and then the other is the log with base 10. So if we have the base e, we have natural log, so log of the natural number ln. If we have the common log, our base that we calculate in is a base 10 system. And so we don't write the base, then we know it is just log. Okay. So let's take a look at example 6 here and see a variety of things that this is coming up with. So putting things together. Let's find the domain of the logarithmic function f of x equals the negative natural log of x minus 2. Okay, so we know that any time that we have a logarithm, whatever we're of, the log base something of, okay, that of piece always has to be positive. So we know then, let me get my pen back, we know then that x minus 2 has to be bigger than 0, Therefore, x must be bigger than 2. So in my domain, I'm going from 2 out to infinity. Letter B, let's graph the function. Okay, so let's graph f. Okay. So as we graph our function here, one of the things that we would have is that we would know overall certain key pieces. So we know at 1, okay, at 1 we have 1, 0. Okay. And out here, let's see, that'd be 2, and let's go 3. So E is going to be somewhere in here. Remember, E is approximately 2.7. Okay, so if I have E, then at 1, I'm at my base. So 1E, it's got -1, okay, -2, -3. So let's see, negative E is going to be right around in here. So that's going to be about -E. And so I'm going to have, whoops, I'm sorry. Yeah, I want E1 to be one of my points. I want 1, 0 to be one of my points. And I want 1 over E with -1. So what's 1 over E? I don't want negative E down there. I want 1 over E. So the reciprocal, let's see, 2.7 is close to 3. Reciprocal of 3 is 1/3. So we're going to be down over here somewhere. It's right around over in here. So 1 over E. So 1 over E approximately here. Okay. Over here, that's the x value. So the y value is going to be -1. So we end up with this being our logarithmic graph of our parent function. So this would just be e to the x. Now we want to go ahead and say, well, let's go, I'm sorry, that's not e to the x. That's the natural log of x. Okay, so that was the natural log of x. Now let's go ahead and take a look at, let's see, we've got a negative out here. Let's take the negative. So that's going to be a reflection over the x-axis. So if I reflect that over the x-axis, then I'm going to end up with 1 over e, let's do this, 1 over e positive 1. So somewhere around in here, okay? So I got 1 over e positive 1. Then I'm going to end up still with 1, 0. Then I'm going to end up with e, so there's approximately e negative 1. So that would end up being the reflection over the x-axis. And then let's see, if I've got this -2 out there, that's applying to the x. So that's going to be a shift 2 places to the right. Now, sometimes a student might ask, so does it matter which order I do these in? I need to do everything in here with the x's and stuff first before I would do any like +3s or -4s or anything of that towards the end. Otherwise, it doesn't matter here. So I'm going to shift this 2 places to the right. So if we shift this 2 places to the right, let's see, this is going to be 2 plus 1 over e. So let's see, so 2 plus 1 over e is going to be about 2 and 1 over e is going to be about in here, so that's going to be 1. That's going to be 2 and 1 over e 1 as far as the value. I'm going to end shifting 1, 0 over to 3, 0. It's going to have e -1, so it's going to be 2 plus e. So it's approximately here is 2 plus e -1. So 2 plus e -1 is going to be in there. Since I shifted everything over to the right, I'm also going to shift my asymptote over to the right. So I'm going to look something of this sort. Okay, so that's going to be my overall graph. Let's see, letter C, I'll put this up here. From the graph, determine the range and the vertical asymptote f. Well, we already did the vertical asymptote. So the vertical asymptote, I shifted over to the right too. So my vertical asymptote is x equals +2. My range here, the range, just like the range of any logarithmic function, is going to be all real numbers. Okay. Letter D, find f inverse. So let's go ahead and find f inverse. I'm going to go ahead and move this down over here a ways. So letter D, find f inverse of x if, let's see, what was f of x here? Our f of x was negative of the natural log of x minus 2. So if we go back to how we were finding our inverses, we had several steps. We had 4 steps. So the first step was to go ahead and rewrite f of x as y. So we got y equals the negative of the natural log of x minus 2. Second step was to interchange x's and y's. So remember, when we're doing inverses, if xy is on one function, then yx has to be on the inverse function. So we got to flip-flop positions. So x has to be a negative natural log of y minus 2. Third step, now we have to solve for this y. Okay, so let's see, if I get rid of this negative, move it to the other side here, then I have negative x equals the natural log of y minus 2. By definition, what this means then is this means e to some power. E to what power? E to the negative x power has to equal y minus 2. Solving this further for y, I got to add 2 to both sides. Got e to the negative x plus 2 is y. And then what that means then, or the last step of the inverse calculations, I replace the y with f inverse notation. And I'm going to flip-flop these around also. So e to the negative x plus 2. There we go. So that is our inverse. Okay. So let's find the domain and range. Okay. So letter E was find the domain and range of the inverse, and then we're going to graph the inverse. Okay. So let's see here. So on letter E, the domain and the range. Okay. So when we're doing our exponential functions, there are no restrictions on our domain here. So that's going to be negative infinity to positive infinity. And as far as our range, well, let's see, this is the inverse. Okay. So normally in, we'll get back to the inverse here in just a second. In our exponential function, okay, normally we go ahead and we hug along the x-axis and then we move up. So we have a horizontal asymptote here at y equals 0. Since we have this plus 2, what that means then is we've moved our asymptote up by 2. So y equals 2 is our horizontal asymptote. That means our range then goes from 2 to infinity. Now, one thing to note on this one, if we go back up a little bit, in our original function, our domain was 2 to infinity. That means in our inverse, our domain and range flip-flop each other. So our domain of the original is the range of the inverse. Likewise, the range of our original is the domain of our inverse. That will always happen. Those always have to flip-flop in that direction. Okay. Now, the last thing that we wanted to do then was to go ahead and graph the inverse function, so e to the negative x plus 2. So what we'd end up, we could put it up here. The other thing we could do is we could take a look at this graph up here from the original. So that could be our line y equals x. So we know then that what we're going to end up with is this reflection over that line. So we did have a vertical asymptote at 2. Now that means we're going to have a horizontal asymptote at 2. Let me go ahead and change colors here. So at 2, let's do it this way. Okay. So that means if 3, 0 is on the graph, then 0, 3 has to be on the graph. 2 plus e negative 1, that means negative 1, 2 plus e has to be on the graph. So 1, 2, 3, 4. So see, e is about 2.7, so that's going to be about 4.7, so negative 1 roughly up in here. Then we'll also have 2 and a little bit, so 2 and 1 over e, 1. So 2 and a little bit, 1 is going to be about, let's see, 2 and a little bit is going to be up here. So that means my graph is going to look something of this sort. Okay. So that would be my reflection. Okay, reflection over the line y equals x. Let me go ahead and put this back in Desmos here. So let's see, what we had is we had the negative natural log of x minus 2. And then we're saying its inverse here is, what do we say, e raised to the power of negative x plus 2. Okay, so if we graph y equals x here, let's also graph y equals 2 and x equals 2, because those were other asymptotes. Let's see, let's make this one dotted, and let's make this one dotted as well. And now we see that this is indeed the graph of what our functions look like. Okay, so again, on the computer, of course, they look so much nicer than what we're going to be able to do by hand, but we did get a pretty close approximation. If I go back to my function here, a little messy. Okay, if I take it this way, not quite as messy, but we still see that it still has the same basic characteristics as what I'm doing on the on Desmos. Okay, so that was graphing a logarithmic function and its inverse. One of the things I should show you also is how to graph this on the graphing calculator. So let's go ahead and go to y equals. And so let's clear these out. These were some items from our exponential examples. So let's see, on this one, we were doing the negative log, so negative natural log rather. So here's the ln button, so it's the natural log. And we had x minus 2. So x minus 2. And then we're saying that we had e, so e to negative x, and then plus 2. So those were our graphs. And we take a look at them. We see those items there. Now, one thing that the logarithmic graph here did not do very well. Let's go back to our y equals. The blue is the negative of the natural log. There is a vertical asymptote here. Okay, so the graph is not going to show that. So this blue piece really goes up and almost follows this exactly along. Okay, it's so close here for our graphing calculator, it has a hard time graphing that. So it is one caveat of when we graph. We have to at least be familiar enough with the graphing calculator to know that it does have some limitations here. Now, if I would go ahead and zoom, let's zoom out here a little bit. Let's see if that will go ahead and fix it. Really doesn't fix it at all in there. So let's go ahead, let's zoom back in. Whoops. So let's zoom in and let's see if we can change that a little bit. Does it move anything around? It doesn't look like it moves up over there a little bit. Now, the odd thing about the graphing calculator is I can't just drag it like I was trying to do, like we do on the computer, but it at least shows a little bit more of that moving up. So I might go to the window here and say, well, let's let my x values, let's get those maybe from 0 to 5. We'll go up by ones. And my y values, let's maybe go from -1. Whoops, I know what I did. Instead of hitting negative, I hit the minus key. So I need to hit the negative key. So instead of hitting negative, I hit minus. So y min is negative. Let's do our y max at let's see, 15. Okay, and we'll count by 5s here. And now let's go ahead and graph. And it still has some issues trying to get beyond up over here. So it doesn't quite show that we're going up past this value. So we do have the asymptote here. So again, just a minor issue with the calculator just to be aware of. If we take a look at the Desmos, there's no issue. Okay, it just shows it. Okay, but Desmos is a newer item that has the entire the internet is working for it, and the PC or the Apple product doing well. So let's, it referred to the common log. Let's go ahead and now take a look at the common log. We're almost finished up here. We need to take a look at some common logs, and we want to solve logarithmic equations. So as I alluded to earlier, if we have the log with no base listed, if there's no base listed, then that is the common log. Okay, and that means that we have a base of 10. So let's take a look then at example number 7. Let's go ahead and graph a logarithmic function and its inverse again, only now we're going to be graphing with the common log, so base 10. So find the domain. Okay, so our domain, again, this position in the logarithmic function must be bigger than 0. So that means x must be bigger than -1. So our domain is all x such that x is bigger than -1, or if we're in interval notation, we're doing from -1 to infinity. Letter B, we want to go ahead and graph this function. Okay, so let's see. Our parent function here is just the log. Okay, we're going to say our parent function is the log of x. That means then that we're going to go through 1, 0. Okay, we're going to go through 1, 0. We're going to end up going through our base at 1. Okay, so it's our base 10 at 1. Okay. So there is 10, 1, and we would have the reciprocal of our base -1. Okay, so the reciprocal of our base is 1/10, so 1/10 -1. Oops, not connecting here. There we go. Okay, so that's going to be our logarithmic function, and of course we have this vertical asymptote at x equals 0. Now, as we take a look at the rest of our graph here, one of the things that we do see is we have this -1, so that means a shift 1 right. So let's see if I'm going to take this over. I'm going to shift 1 right. So now I'm going to graph log of x minus 1. So if I shift over 1 right, then my vertical asymptote shifts over 1. Okay, and then I'm going to have, instead of 1, 0, I'm going to have 2, 0. Instead of 10, 0, I've got, certainly, instead of 10, 1, I'm going to have 11, 1. And instead of having 1/10 -1, I'll have 1/10. Let's see, if I'm moving it 1 over to the right, that'd be 1 and 1/10. So 1 and 1/10 -1. So it's not 1/10 there. It's 1 and 1/10 -1. So this value is -1. That value is -1. And so now we've just shifted things over. Now we've got this 3. That 3 then is a vertical stretch. A vertical stretch of 3. That means I'm taking all my y values and I multiply them all by 3. So I still have my vertical asymptote here at x equals 1. I'm still going to have over here 2, 0, because that's not going to change. But out here at 11, instead of being 11, 1, I'm now going to be 11, 3, because I multiply my y values. Okay. And then down here, I was going to be at 1 and 1/10 -1. Now it's going to be -1 and 1/10 -3. Excuse me. Yeah, so -1 and 1/10 -3. So now let's see. So it's going to stretch it, going to make it open up a little bit taller as we go through. So that ends up being my graph here. So this is 3 times the log of x minus 1 base 10. Okay, so as we take a look at that, we can identify some parts and pieces, and this is going to end up being letter C here. Letter C, we're going to say what's the range. So we know that our domain was, let's go ahead and write this down here. Our domain was from 1 to infinity. Our range here in a logarithmic function is from -infinity out to positive infinity. So how low do we go? We still go down to -infinity and come up to positive infinity. And our vertical asymptote, well, we've already listed. So our vertical asymptote, we'll say here is 1. Now let's go ahead and find the inverse. Okay, so let's find the inverse here. So that is letter D. Find f inverse of x. Let's go ahead and write this back down. If f of x was 3 times log of x minus 1. So again, our steps in this, I'm going to get some more space here. The steps that we were referencing would be go ahead and rewrite the f of x as y. So we got 3 times log of x minus 1. Then I'm going to replace x with y and y with x. So x equals 3 times log of y minus 1. Let's divide both sides by 3. So we got x over 3 is log of y minus 1. So what this means then is that we would have log with base 10. So 10 to some power, 10 to what power? 10 to the power of x over 3 is y minus 1. So we have 10 to the power of x over 3 equals y minus 1. That means y is 10 to the x over 3. Our last step to find the inverse is to replace y with f inverse notation equals 10. Oops, I forgot my plus 1 over here. Sorry about that. I think I said it, just forgot to write it. I would add 1 to both sides. Then I would go ahead and rewrite this. So there's my inverse function. 10 to the x over 3 plus 1. Okay. And so the domain and range, okay, so we come back up over here. Okay, letter E. Okay, so on letter C here, this was log of, 3 times log of x minus 1. Now we have our inverse. So our inverse function now is 10 to the x over 3 plus 1. So let's figure out our domain and our range. Well, in this scenario, what we can see here then is that if our inverse, our domain was 1 to infinity, now our range in the inverse, or this other function, must be 1 to infinity. And then whatever our range is now becomes our domain. So we can go ahead and take 10 to any power that we want. So we plug x in here. Doesn't matter at all. Plug any x in you want, divide it by 3, and 10 to any power will always be positive. Then if we add 1 to it, okay, so the lowest we can get to is really close to 0. Okay, so we'd end up with that asymptote at 0, but then we'd have to move it up by 1. So my range then is going to end up being 1 to infinity. Okay, and so my graph overall with my exponential, it's going to look something like this. Here's y equals 1. So I have a horizontal asymptote. Then I would just take the reverse values of all of these. I'm going to end up with 311. So 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's 311. 2, 0 is going to be 0, 2. And then negative 1 and 1/10, negative 3 is now going to be negative 3. I'm sorry, that should not have been negative 1 and 1/10. That should have been positive 1 and 1/10. So make that correction up here. That should have been positive. I graphed it correctly. I just noted it incorrectly. Okay, so we'll make a quick fix on that one. That means, let's see, if I had 1 and 1/10, negative 3, now I got negative 3, 1 and 1/10. So that's going to be my exponential function. So again, those points just reverse off of what that other function is. Now, one of the things, just as we have a question like this in our homework, so I'm going to go to that homework and take a look at that. Let's go ahead and find this up and through here. I think it was question 9. Yeah. So I want to take a look at question 9 here. Now, in our homework, semester by semester, these might get scrambled a little bit. So when I'm taking a look at it currently, it's question number 9. In a different semester, it might be question 10 or 11. Maybe it's question number 8. So it is going to be one of these that takes a look at the graph. And that's the thing that we want to do. So we want to graph 1/6 to the x power. So that's the exponential function. So I'm going to click the graph button. The exponential function. Look up here in the template. Okay, so I've got the line tool, absolute value tool. So I just hover over these. I see what they are. Logarithmic tool, exponential tool, circle tool. We have our shading tool, and then whether we want our line to be solid or our line to be dashed. What we want is we want to graph 1/6 to the x. So that's an exponential. So we want this one. So we're going to click on the exponential. Click anywhere on the graph. Doesn't matter. It'll automatically snap in here. We want our base to be 1/6. So I'm going to come down over here to the base, down here towards the bottom. I'm going to change this to 1/6. That's that graph. Okay. Now, I also want to graph the logarithm of x with a base 1/6. So on the same graph then, I'm going to come up here. That's the exponential. Let's do the logarithmic. Again, doesn't matter where I click it. I just got to click it in here. And my base here, I need to change again to 1/6. Now, if I needed to do any stretches or compressions or shifts one way or the other, or do some reflections, I can do those in here with the menus. All I have here is a basic graph. So I have both of those on here. Now, what's interesting, if I go ahead and blow this up, they're very, very similar to each other. And this is one of the items that I've got questions in the past from students. It's like, it looks like I have the right graphs. What have I done? So the typical thing that changes here, if I click on this one, for instance, they didn't change the base. So the base was still E, or the base was 5, or the base was 1. We've got to change the base to the correct value that we have up here. Okay. Then we can go ahead and check our answer. And excellent, we've got it. Okay, so just wanted to bring that to your attention. So we start with the graph tool, and then we go from there. Last objective here is to solve our logarithmic equations. To solve the logarithmic equations, we're going to use the definition of what it means to be a logarithm. Okay, so a logarithm. So let's say we have log of x base b equals y. That meant then that b to the y had to be x. Okay. So we have whatever the logarithm equals is the exponent. So over here, if we have log of 4x minus 7 of base 3 equals 2, that means our base is 3, our exponent is 2, and that has to be equal to the 4x minus 7. So what I did at the beginning of the lesson was this. Still holds true, only now we have something we can evaluate. So that would be 9 equals 4x minus 7. If I add 7 to both sides, we get 16 is 4x. If we divide by 4, then x equals 4. Now, one of the things we always need to do is we need to go back and double check that that does fit within the domain of our logarithmic function. So the domain of our log means that 4x minus 7 has to be bigger than 0. That means 4x has to be bigger than 7, or x has to be bigger than 7/4, and 7/4 is 1 3/4. So as long as x is bigger than 1 3/4, then we're okay. We're saying x equals 4, so we're fine, because 4 is bigger than 1 3/4. We take a look at log of 64 base x. That means x squared must be 64. So if we take the square root of both sides, that would be x equals plus or minus 8. Now, again, we have to double check. Okay, our domain here. Okay, our domain here, well, is 64. So that's fine as far as that component. But one of the items that we caveat is whatever our base is. Okay, so our x. Let's go back up to the very beginning up here. Okay, our a value here says we have a base of a with x. Okay, and did we have any restrictions on a up in here? Yes, we did. We had a had to be bigger than 0. So part of our definition, where was a? A was our base. Okay. So a was our base here. So that base had to be bigger than 0. And then also what we, well, we'll go ahead and stop it there. So that a had to be bigger than 0. So when we come back down to the bottom, a lot of stuff to scroll through here. Okay. This x has to be bigger than 0. So since x has to be bigger than 0, the negative doesn't make any sense. So we could say our base just has to be 8. Okay. Last example, let's solve something with a base of e. Okay, so the base of e, that means, let's see, we can rewrite this. We can say the natural log. So log of base e. Okay, so e to some power, so natural log here, also write it log base e. So our exponent here is 2x. Okay, and let's see. Oh, yeah. So our base here, okay, so our base Yeah, so our base, we start here. We've got this coming up over on this side. So e is our base. Okay, we pick up the 5 and we land at the 2x. So the other way to write that is natural log of 5 is 2x. Remember that the logarithm equals to the exponent. Okay, so we have that position there. So I can either use log base e or I can use natural log 5. Let me use natural log 5 because that's what we're set. That's the more common way to phrase that. So I've got natural log 5 equals 2x. If I divide both sides by 2, then we end up with x. And that one's done. That would end up being the value, or we could say that's the 1/2 the natural log of 5 if we want to phrase it that way. So natural logarithms, inverse of the exponential function, that's what we were taking a look with overall in this particular scenario, in this particular lesson, I guess I should say. So if you found a mistake that I did not catch along the way, please email and let me know. Otherwise, that wraps up Chapter 6, Section 4 on logarithmic functions.